Right. So, sorry for not posting anything in those little amount of hours. Anyway, the thing was that I was not feeling well, and yeah, so everything got delayed. Anyway, I did post something, but just not about this book particularly. Anyway, so we were at 13th question, right? We got this. Oh yeah, and by the way, uh, I just found out that this B thing, right? So fourth B, it was not supposed to be like this. So the thing is that I didn't actually scale up one of the x's. So each unit corresponds to some value. I didn't do one of them. I think I did the other one, but not the yeah. So two, right? X and y axis. So I had to do that one as well. Anyway, so other than that, the 13th one, right? So we did it definitely, and it was yeah, it wasn't good at that time when I was doing it because yeah, this question is really, I mean, complicated. I made a whole video on this thing. So that will give you the clarity of how to solve these questions. Actually, even I didn't know how to solve questions like these, where your velocity vector changes with respect to position of the two particles. So you have to first completely find out the geometry. Like for example, in quaternary problem 2, you had to figure out something about the geometry before actually figuring out the forces and tension and everything. Right. So the same kind of thing over here. So just divide two differential equations, and if somehow you can cancel one of the variables, right? So in this case, for example, your dt can be cancelled when you divide the two differential equations, and then you get something nice. I mean, not exactly nice. It's still very complicated because you have to then solve it and then input that value into the original differential equation to get the time dependence. Yes, but at least it's solvable. Anyway, so 13th is done. Let's go to 14th. New page. Right, 14th. A train of length something starts moving rectilinearly with constant acceleration 3 into 10 power negative 2 meter per second square. T equal to 30 after the start. The okay headlight is switched on. Okay, let's just write this down. So the length is 350 meters. So that's SI units. Rectilinearly with constant acceleration 3 into 10 power negative 2 SI units. T equal to 30 after the start. The locomotive headlight is switched on. Okay, so that's event 1, and tau equal to 60 seconds after that event, the tail signal light is switched on. Okay, I get that. Find the distance between these events in the reference frame fixed to the train and to the earth. Oh, so you have to do two things. How and at what constant velocity v relative to the earth must a certain reference frame k move for the two events to occur in the same point. Okay, so not that complicated, right? So let's just go with the ground frame first of all. So this thing, the train is moving with what velocity? Okay, so it's not velocity. It's initially it is what it's at 0, right? Constant acceleration. So after the start, at start your yeah, so speed was 0. So t equal to 30 after this thing, your velocity will just be so call the thing u1. That will be this times that. So 9 into 10 power negative 1. So 0.9 meter per second. Right. And then in the next tau is equal to 60. Right. So you just have first of all the front headlight, right? That will get on, and then the second headlight. So 60 seconds later. Right. So it's at say position A. At A, this headlight is on, so this is where the event 1 happens, and then in 60 seconds it will have moved maybe somewhere over here, and then this is B, something like that. So in 60 seconds what will be this thing's displacement? So ut this times tau is 60, so yeah, 9 times 6 54 minus half t square, so half 80 square, so 3 into 10 power negative 2 upon 2, and then t square, so t is just this thing, so 3600, that 100, 36 into 3 upon 2, so 18 into 3, which is 54, I think, and that's just equal to 0. So that means, wait, what, how can that be? Oh, sorry, this is the Sorry, wait, you are saying it doesn't no, that can't be. Your okay, u1 was 0.9, right? So ut, and that should be 0.9 times 6, well that's 54, minus half at squared, so a is it's positive acceleration, right? Yes. So oh, it should be positive, of course, ut plus half at, so not negative. So yeah, this is just going to be 108. So 108 meters is the displacement. What's l was 350, so this minus that's, I mean, yeah, this A point moved 108 in the front, but then 350 minus 108 is still remaining, right? So B will be at that. So what I'm saying is that the train will have moved something like this. This completely is just 108, but then this thing, so B is somewhere over here. That is 108 minus 350 minus 108, which is 242. So 242, that's the distance between the 2 points. So event 1 and event 2. So at ground frame, how do I write this? I'm gonna write it like this: ground frame, or just ground, whatever. So the distance between A and B, that is 242 meters. What about the reference frame of what? Fixed to the train, of course. So, with respect to the train, of course, L is the distance, because wait, no, wait, this point, wherever this that's kind of weird, because so the point where it happens, that point is fixed to the ground. Let's just say that means that point is uh, moving back, basically, right? So this is our train. According to the train, the point where you have event 1 happening, that point is moving back with, yeah, so yeah, U and A, like in this direction. And so that's where the front headlight went, right? That's a point which is moving back, exactly. And then after time equal to 60, right, this will happen, this B point, it will, okay, not bad, it's still doable. No, so in fact this distance is still the same, right? Yeah, I mean, of course, inertial things, so distance is still the same. It doesn't really matter if it's not inertial, it's still the same distance, because doesn't matter in what frame you do this point and that. Wait, but is this how we do it? Is this point supposed to go back, or do we just have this point sitting over here? Huh. Wait, what? So does the point of event 1 go back or not? I don't know. I mean, if we were on the train, what would we think? That it would just be the length, right? Only the length is what's the distance between them. So the point is not supposed to be moving, but this feels wrong somehow, because, oh, this is weird. Right, so event 1 happened over here, and then we just forget that, yeah, it's moving. We just forget it's moving. According to us, event 1 did happen over here, and it's just at that position, right? It's not moving. So then in that case, length is the thing, so L. So this is going to be 350 meters, hopefully. Okay, and now what we want is some reference frame that moves such that these two events happen at the same point, right? Wait, that reference frame should move with what? Oh, it moves with a constant velocity. Okay, constant velocity v. Fine. So call it v. So u1 minus v times t plus, usually tau plus a upon 2 times tau squared. That's the displacement that that the train will go through, right? Oh yeah, so according to that guy as well, the point where light bulb went on, that is not moving with respect to him, I think. So that's how we have to assume, right? Oh, so in that case, it is not bad at all. I mean, right. So this thing is like, okay, this went on, and then after the 60 seconds, it went here, and this went on, right? So L is equal to this thing, basically. Cool, no problem. We already have what u1 tau. Okay, that's supposed to be 108. Yeah, and then minus v tau. So we don't know. Tau is just this thing, 60v. And that should be equal to the length, which is 350. Hey, we know what this thing is. So 60v is equal to... Oh, wait, why? Why is this? V should be negative, it seems. I mean, yeah, so when it was in the ground frame, you saw that train didn't actually pass that point. Right, so that makes sense. It didn't actually pass A, so we need to speed that up. So that means, yes, V should be negative. So this is once again just negative. What was this thing? 242? Why is this? Yeah, it is 242. So V is just negative 242 upon 60. Do we put the negative sign in there or not? Relative to Earth, I'm just gonna put the negative sign. So negative 242 upon 60, that's the answer, which is just negative 121 upon 30. Yeah, that's a reduced form. Okay, so just put that here. V is equal to negative 121 upon 30. Weird question was full of assumptions. Next, 15th. What is an event in the first place? Like, okay, you have that guy's coordinates. Do those coordinates remain constant or not? I think they do. Just like how we do in special relativity, the event's coordinates are constant in space and time, of course. So same thing should happen with you. Whatever. Next question. 15th. An elevator car whose floor to ceiling distance is equal to 2.7 meters starts ascending with constant acceleration 1.2. Okay. So elevator moving up. Floor to ceiling distance is 2.7. Okay, cool. Constant X. Wait, oh, so something like, right, this is the elevator. It is this thing, the length of the elevator, right? Right, that thing is 2.7 meter. Ah, okay, that makes sense. Yeah, you could just think about each floor being very thin. So it's just like, I know it's not supposed to happen because the floors have thickness, but we'll just say, okay, there's no thickness. Because actually what's happening is that these floors, this distance is what's 2.7, but since they didn't actually tell us how the floors are, if it's thick or not, we'll just say, okay, these are just thin slices, and then the elevator is going up, its length is what is 2.7. Ascending with cos acceleration 1.2 meter per second square, whatever. 2 seconds after the start, a bolt begins falling from the ceiling of the car. Okay, so right now it's at rest, I think. So in 2 seconds, this will be 2.4 meter per second. That's how it, right. Find the bolt's free fall. Okay, so I think it's at ground floor or something, right? And then a bolt loses. So this is like, this is how the elevator is. Its distance is 2.7. It's going up after some time. So I don't know what time. It just goes up over here or something. It's moving with some velocity upwards. A bolt loses. So this bolt is also now moving with that velocity, and but it's not the same acceleration. So this guy just go up, but then this won't catch up with it, and it will just go like this, fall down. Fine. Right, so we want to find the bolt's free fall time. No big deal. Come on, just need to figure out the height and the velocity, right? Yeah. Okay. And what else? Displacement and distance covered by the bolt during the free fall in the reference frame fixed to the elevator shaft. Wait, what? Fixed to the elevator shaft, huh? Oh, so it's a pseudo force and gravity acting on it. Fine. Not that complicated, I think. I mean, okay, the second case is in fact easier. That's the first time pseudo force is making things easy, right? So this is going up with acceleration 1.2, and g is let's just say it's 10. So 10 is acting on this, and then 1.2 is also acting on this, and we want to find displacement and distance covered by bolt during free fall. Oh, okay, we still need to figure out the time required for the free fall. Come on, seriously. Fine, we'll figure out what that time is. Right. So find the height attained by this. It's at 0, so starting it's just 0. Acceleration this thing, so half a square, that's 0.6 into t squared. E is just, okay, so into 4. So 2.4, that's our height. And what's the initial speed? This is u, I think. U is this times that, yeah. So that is also 2.4. Well, that's nice, I guess. Right. Oh, it's the ceiling. Okay, so height is not this thing. Instead, it's this plus 2. Wait, wait. Oh, okay. I think when it says it is falling down, it's falling down to the floor of the elevator, not of this pit, the elevator pit. In that case, it is actually even simpler. Fine. So then we just do it with respect to this elevator. With this elevator, there's this. What happened? Okay, sorry. So there's just pseudo force, pseudo acceleration 1.2, and well, okay, so it's gonna be 11.2, or in fact, since it's that precision, say 1.2 plus 9.8. Exactly. Nice. So 110, 1.0. So 11 is acceleration downward. The length is 2.7. So yeah, half 80 squared, half into 11 into t squared is equal to 2.7. There we go. It should be easy. So t squared is equal to, well, 5.4 upon 11. About 5. So square root of that. I have no idea why you want to calculate this thing. But hey, square root of this thing. That's it. That's our time. So the bolt's free fall time. So it's not even like doing complete motion, it's just falling down. Hey, this was easy. It's ascending, it's not even descending. Even if it was, it's still the same kind of thing. So that's it. A is just square root of 5.4 upon something like 54 upon 110. No, let that be. Or you can multiply by 5 maybe. So 25 and then so 27 upon 55. Nice. And B, what's D? The displacement and distance covered by the bolt during the free fall in the reference frame fixed to the elevator shaft. Come on. So fine, it's the same thing, 2.7. Both have the same answer. That was easy. Right, next. Falls from the ceiling, right? So has to be like that. 16th. Two particles want to move with constant velocities v1, v2 along mutually perpendicular straight lines towards the intersection point O. So let's draw it now. This thing is O. v1, v2 are mutually perpendicular straight lines towards the point O. So maybe like this. This is v1 and this is v2. At t equal to 0, the particles were located at distance L1, L2 from the point O. Okay, so this thing was L1, this thing was L2. What then? How soon will the distance between the particles become the smallest? What is it equal to? Oh, something like that. Fine. So, yeah, we can just figure out what the coordinates of these points. So this guy has the coordinate L1 minus, it should be V1t minus L1 comma 0. This guy has the coordinates 0 comma V2t minus L2, right? And then just find a distance between them. So square root of, yeah, you get the idea. We just want what? At what time, right? Yeah, how soon? Same thing. Yes, and what's also it's what is it equal to? It's, in fact, let's just find distance squared first of all, not that. So this and that. Oh, it's square of this thing. Nice. So v1 squared t squared. Oh, I see what's gonna happen. It's some kind of ellipse. I mean, not exactly like that, but you get the idea that. Fine, just do it. Just do it the normal way. So v1 square t square minus 2lv1 t L1 squared. It's not ellipse, but what do I even say? What it is? 5 plus v2 square t squared minus 2l2 l1 l2 sorry v2t plus l2 squares. Just want to do these things. So v1 squared plus v2 squared times t squared minus 2 times of l1 v1 plus l2 v2 t plus L1 squared plus, yeah, you get the idea what's happening. So the thing is, for this to be minimum, what should happen is that t should be equal to minus v.2. So just L1 v1 plus v2 L2 upon 2 times of v1 square plus v2 square. There we go. Do I need to calculate? I mean, okay, negative d upon 4a, how bad could it be? Oh, it could be really bad actually. Fine. So, first of all, we can definitely tell how soon they will collide. So t is equal to this thing, right? L1 v1 plus L2 v2 upon v1 squared plus v2 squared. Nice, actually. All right, and we also need to figure out what negative t upon 4a is for this equation. That would be the value of this thing, but then actually the square root of that is what we are going for. Right, so negative t, negative of t square, this thing squares 4 times of this L1 v1 plus v2 L2 square minus 4ac. Why are we doing this? It's going to be so bad. Fine, just do it. Minus 4ac, so minus 4 times of L1 square plus L2 square and then v1 square plus v2 square. I can see what's going to happen, yes, but this will be so painful. Okay, upon 4a, so 4 times of v1 square plus v2 square. This is how it's going to be. Nice. So yeah, this cancels, and then it just becomes this times that, which is L1 square v1 square plus L1 square v2 square plus L2 square v2 square minus, sorry, plus L2 square v1 square. Oh, yes. Okay, minus this thing squared. So minus L1 squared v1 squared minus L2 squared v2 squared minus 2L1 L2 v1 v2. Right, it's a numerator. And look, this and this will cancel. This and where is it? This will cancel. Good. And now this and this will just be L1 v2 minus L2 v1 squared. Right, and that thing upon this quantity, so v1 squared plus v2 squared, and now we just need to take the square root, so this will just be d is equal to L1 v2 minus L2 v1, the mod of that, of course, yes, and square root of v1 squared plus v2 squared. I have no idea how accurate this thing is, but that's what we got. Next, seventeenth is from point A located on a highway. One has to get by car as soon as possible to point B located in the field at a distance L from a highway. Okay, distance L from the highway. So this is, what is it? Right, this thing is the highway, I think, and this thing is a field. Huh? A is somewhere over here, I don't know. One has to get by car as soon as possible to point B located in the field at distance L from the highway. It is not that. Okay, so the highway should be thick, I think. Wait, first when the car moves in the field, this many times slower than on the highway. At what distance from point capital D? Why? What's capital D? They didn't actually tell us. One must turn off the highway. Huh? What's capital D? I have no idea what capital D is. I think they want capital A. So first you'll just go like this and then like this. Must turn off. So in fact, yes, just say that the highway is thin and the field is thick. Fine. So then it's just going like, why is this happening? Like this and then like this, right? And what do we need to find? Yeah, at what distance should we turn off to reach? Yeah, so that it is in the smallest time. So car moves in the field this many times slower than on the highway, right? So if this is speed v over here, then this will be this coefficient times v. Okay, so this distance upon v, and then this distance upon this coefficient times v, that is the time required. And what if it just went like that, huh? Well, this thing should be less than that, I know that. So what we are saying is that, okay, so call this thing d1, d2 and d3, So d1 upon v, okay, skip that. Plus d2 upon this coefficient, that should be less than or equal to d3. But hey, we know that d1 plus d2 is bigger than or equal to d3. Are you thinking what I'm thinking? Right, we could make that coefficient. I mean, we could make this from it, right? Probably. Oh, why do that? We can just do d2 upon this coefficient is less than or equal to d3 minus d1, and then d2 is bigger than or equal to d3 plus d1. All right. Now, you know what I'm thinking? Just divide this because, of course, the reciprocal of this thing, that's going to be supposed to be negative. Sorry. So d3 minus 1 upon d3 minus d1. That's what I'm thinking. So I can just, that's stupid. That's just telling us that this thing is bigger than 1. Come on, that's not helpful at all. Give me some relation between d1, d2, d3. Will you? Ah, this isn't going to help. Okay, you know what? Let's say that we go for coordinate. Okay, maybe that's just the bad idea. Coordinate geometry. Point B, it's somewhere over here. Hey, we don't know. This is L from the highway. Okay, so is this thing L, or is it that this thing is? No, that can't be. Oh, okay. So this the perpendicular distance is L. So then this thing will be L. Fine. What's this distance? We don't know that. And how much along the highway? Something's not correct about this because they didn't give us a diagram and they also didn't give us what this distance is supposed to be. So how am I supposed to solve this thing? Unless of course they give this thing as L, probably that's what. But then the highway is not just the point A, it's this thing. So the distance should be this, right? Figure 1.2. Oh, okay, they did give us a figure. Fine. So this is A, then it move. Okay, and then it starts going like this, right? And this is capital D, huh? Oh, now I get what's supposed to happen. So this distance plus this distance, that should be minimized and call this thing as X, right? That probably will do it. You know what this, right? So you can figure out what that should be. No big deal. So let's say capital A and capital D. So the distance between them is small d. So then we are trying to minimize d minus x plus square root of x squared plus L squared. Just make it instead to go to 0. So negative 1 plus x upon square root of x squared plus L squared. That guy should be equal to 0. So basically x is equal to square root of x squared plus t squared. Hey, this one, not this L squared. Kind of weird, right? So this and this should be, no, that can't be. This can't be. You want it set it to 0, so minus 1 plus, so this is going to be 2 square root of all that stuff, and then 2x. So x upon square root of x squared plus L squared, that should be equal to 0. But what that tells us is, no, this is wrong. But we do want to minimize, oh, okay, yeah, of course. The way to minimize this would be that just put x is equal to 0 if you wanted to minimize the distance. That's not what we want. It's definitely not what we want. Sorry, the way to do that would be, yes, to put x is equal to 0. That's not what we actually, wait, no, that would maximize resistance. Fine. What we actually want to do is divide by v and that coefficient times v. So actually we want to minimize this thing. Fine. So then we will just have this over here. Quadratic, two values, right? Nice. So this will be x squared upon this thing squared is equal to x squared plus L squared. So there we go. At what point from D, right? That's what we need to find. So x basically. So x squared into 1 minus of this L squared, x is equal to L upon square root of 1 minus 1 upon this guy squared. That's it. They just really hit the whole diagram, and I should have seen that they're referring to figure 1.2. Okay, now we know at least. Next, 18th. 18th is a point travels along x-axis with velocity whose projection vx is presented as a function of time by the plot in figure 1.3. So this thing is vx, fine. Assuming the coordinates of the point x equal to 0 at moment t equal to 0, draw the approximate time dependence plots for the acceleration wx, the x coordinate, and the distance. Come on, are you serious? Fine, so just start with the acceleration first of all, because that's the easiest. So over here, the slope is 1, time is in seconds, I assume, and this should be, I mean, everything, I'll just say it's in SI units, whatever. So yeah, slope is 1, acceleration should be 1, and then it drops to 0, so it's like this. Should I draw it better? So this thing is our acceleration, this thing is our time, in x direction of course. And so first at 0 acceleration is at 1 for what, 1 second it remains like that, then it's 0, right? Then it goes like that for 3, and then from there it goes negative, so it's negative, and till what, till 6. I need to clear up some things. So till 6 it remains like that. Make this slightly bigger. Right, and then it will increase. Hey, what's the acceleration? It is -1, right? Because yeah, the slope is the same as thing, but just negative. Yes, so this is 1, this thing is -1 over here, and then it is positive but with slope 2. So there we go. So over here, whatever. Do they really expect me to graph this without graph paper? Okay, and for just 1 second. That's it. And then what? Oh, and then it just goes horizontal, so there's no. Wait a second. Right, so in this region, right, it's continuous everywhere. So over here, your acceleration can't be like discontinuous. It's not possible. The slopes are discontinuous, yes, but acceleration not really. Uh-huh. And then it's 0, so acceleration is also 0 after 7. So that's how it goes. Not acceleration time graph now. Minimize this really hard. Okay, let's go to what now? The displacement time graph. This is just labor now. It's not even fun. Why do they want us to do this? So the displacement and time. Okay, let's talk about 0 to 1 now. Oh, this is bad. The velocity is increasing in linear fashion, so it's going to be parabolic. Oh, why? Why do you want me to do this as a parabola? Are you serious? Okay, so displacement goes to half when this goes to 1. Yes, but this is going to be a parabolic form, and how am I supposed to graph that? This is just, it's just torture. 1 at that point will be half, something like this probably, because t square, so yeah, whatever. Who cares how the graph looks? I mean, I do care about the functions, I just know it's going to be half t square, but hey. Okay, and then what? And then this thing is horizontal, so it's going to be a linear graph. So it goes from 1 upon 2 all the way till 1 upon 2 plus what's this, 1 times 2, right? So 2 units up. Wait, this is half, and then you want me to go up 2 units. So maybe over here, this thing is half, this thing is 2. And in how much of time? In 2. So till 3, it will have gone up 2 units. So over here. And then velocity is negative, so it's going to decrease. Once again, non-zero acceleration. Why do they want me to do this? Okay, so the velocity initially is okay, so velocity at 4 is 0, right? That's all we need to know. At 4 your, wait a second, Oh, uh, yeah. So what happens? So it's like s is equal to bt plus half at square. So and when that becomes zero, what happens? It just becomes half t square, something like that. Okay, this is just really bad. Half at square. Come on, just do this thing. Half at square plus vt. So when is the minimum? That's what we actually want to figure out. So that will be negative v upon 2. So negative v upon 2 times of this thing. Just so whenever it's negative v upon e, that will be your wow. Why do they? But we know that the velocity is zero. That means the slope should be zero, right? Oh, that's ut. Sorry. Yeah, that's ut. Why am I doing this? Right. So at negative u upon a, it at that particular time it will be zero and stuff. So if this was yeah, that's basically at t when the velocity is zero. That's where we are talking at, right? At this point, it will be the minimum. It's decreasing. I think it's downward parabola. I think so. Right now, the slope is positive, so it's gonna keep on going like that. And hey, wait a second. The slope is supposed to be positive. How can this be just discontinuous like that? That is not. It's what? It's half t square. And how did this slope go? Like okay, so this is supposed to be what slope two looks like, and no, but it's v is equal to 1. It should be a slope of 1. And at t equal to what? So it's like half t squared. Yes, it's supposed to be 1. That is correct. It's correct, of course. But this doesn't look like 1 in any way. Ah, why? Why do they want me to do this? Okay, so maybe this is supposed to look more like 1. Okay, we'll do it. We'll do it. Just make a better graph. Huh? What is happening? Why is this? Okay, so 3, squeeze it over here because this should look about the same. I don't believe it. Now they want me to graph things really nice. Seriously. Why? And something like that. That's how it should be. I know it's a parabola and all, but it really just looks like a line at this point. So the slope is 0 over here and then it goes to 1. Something like that. And then it will be 1 for some time. At t equal to 4, you will have a maximum for this. And then it will start decreasing like a parabola. Right? I just don't want to do this. Fine. So over here, this thing, this displacement is even more. So it's like half plus half 1. 1 plus 2. So 3. Till now it's displacement 3 in this thing. And then, yeah, so this whole area should be 3. Sorry, no, the displacement is 3. So this thing will be 3. Alright. And then what? Will start decreasing. What's this area? This is 2. This thing is 2. So minus 2. We go back to 1 in that case. So somewhere. Okay, so this is looking horrible. But you get the idea. Now it's gonna be parabola and it goes down and then once again at this point your velocity it's discontinuous. Wait, what? No. No, the velocity is not okay, fine. The slope of this thing is not discontinuous right now. So it's at negative 2, so it's still decreasing. But now the acceleration changes, so now it's upward parabola. So I have to start going up, and then at 7 it will reach the maximum. Sorry, the minimum. So at 7, this thing is 4. That's it. I'm not gonna do anything more for this problem. What did I expect me to do? Okay, 19th. A point traversed half a circle of radius something during time interval this much. Calculate the following quantities averaged over that time. Half circle during time interval something, calculate following quantities averaged over that time. The mean velocity averaged over that time. velocity. Nice. Which is that displacement. So what's this? 2 times of that, right? 320, that upon 10. There we go. 32 is the displacement in that direction, of course. So A is 32 magnitude, right? B, the modulus of the mean velocity vector. Oh wait, they do want me to actually express this as a vector, huh? But uh wait, what's the difference between these symbols? This thing, is this supposed to be magnitude? Uh Look, is this supposed to be speed or is this supposed to be actual velocity? Because you are using different notation over here for some reason. Velocity of the mean velocity. Okay, mean velocity vector of the total acceleration. Okay, so B and C are vector quantities at least because they want the modulus. And I'm assuming A is already a magnitude. So then it's not correct. Then they probably want mean speed. So pi r, which is pi times this thing, that upon that. So 16 pi centimeter per second, whatever that is. And then this quantity is supposed to be 32 centimeter per second. And C is what? Modulus of the mean velocity vector of the total acceleration. Come on, serious, total acceleration. So, wait, we don't know what the velocity is initially or finally actually. So how am I supposed to find this out? Okay, if the point moves with constant tangential what? Constant tangential acceleration. Oh, okay. This is bad. We know that thing, right? B square minus U square is equal to 2s. We can just use that, I guess. So 2a dot s, and we don't know what that. Okay, this is just bad. Hey, it's constant tangential acceleration, you say. So initially its velocity was, if it was moving along that circle, its velocity was always tangential as well, because its radius isn't changing. So then it's just this to that. Oh, then it's actually doable, right? So s is equal to ut plus half it square. That should be doing it, I guess. We don't know what u is, unfortunately. Oof. Right, with different initial speeds, you have different things going on. What am I supposed to do now? During this time interval, of course. You don't know what the acceleration is, you don't know what the initial speed is. You are stuck. Unless, of course, you assume that initially it was at 0. Then yeah, it is possible to solve this. But oh yeah, so the mean, okay, mean velocity is actually doable, and this thing is also doable. Yes. Mean velocity vector. You can figure out the time required. Yes. That is already given to you. You can figure out what v plus u upon 2 should be. Yes, that's all doable. But the problem is that without initial speed, you cannot figure out what this thing should be, right? It's just not going to happen. So C, I don't know. So leave a question mark. 20. A radius vector of particle varies with time t as r is equal to at into 1 minus alpha t, where a is a constant vector and alpha is a positive factor. Okay. Radius of a particle, radius vector. So the vector varies like this. Okay, no big deal. So okay, fine. It's just not changing its direction because a vector is giving us the direction. Right. Find the velocity v and the acceleration w of the particle as functions of time. Come on, seriously. It's just what this thing is. Whatever a hat is, we don't know what that is. Then you have magnitude of a. Call this thing a. Just simply a. a times t minus a alpha t square. So this comparison, right, you can clearly see that a is the initial velocity and it's basically decelerating at this point, right? It was going like this, now it's decelerating. And the acceleration of the particle as functions of time. Okay, so you want vector functions, fine. It's not supposed to be like this, it's supposed to be like that. So yeah, no big deal at all. So your v vector is just equal to a vector. Okay, this is problematic because I can't use that. So you will have to use w for this. And that's just equal to, so it's supposed to be negative half of a vector, so w vector t square. So half w vector is equal to this thing, w is equal to negative 2 times alpha, so negative 2 a vector times alpha. There we go. This was easy and unnecessary as well. What was this question once again? 20. That's all you want to find, right? Oh, so b is also. So time interval by the particle to return to the initial position and the distance as covered during that time. Fine. So basically, like if this was thrown up, find the maximum height and the time period. So what was the initial velocity, right? Oh, so v you need to find as a function of time. Sorry. So this should just be negative 2 a vector alpha times t. That would be correct. What I found out before was the initial velocity. Yeah, it's constant acceleration, really nice, right? So what do we have? Initially it's just a vector, so 2 magnitude of a, so 2a upon the acceleration magnitude of course, which is just 2a alpha. That's supposed to be 1 upon alpha. That's the time required for it to go back. So 1 upon alpha, huh? Okay, this thing is for section A. For B, it's 1 upon alpha. That's delta t. And what else do you want? And the distance s covered during that time. Come on. So yeah, when is this supposed to be equal to 0? When you have t is equal to 1 upon 2 alpha. So in that time, what's the displacement? It's just plug that in this thing. So yeah, 8 times off. Oh come on. 1 upon 2 alpha. And then 1 minus of 1 upon 2, I guess. So just 1 upon 2 once again. So it's supposed to be a vector upon 4 alpha. That would be your displacement. So the total distance is just a upon 2 alpha. Yes. Maybe like magnitude of a vector. That would be better. Where did it go? Where did it go? Yeah, it's just S. Fine. Next question, 1.21. So 21. At the moment t equal to 0, particle leaves the origin and moves in the positive direction of x-axis. T equal to 0, it leaves that, moves positive direction of the axis. Fine. Its velocity varies with time, like this thing where this is the initial velocity vector whose modulus equals v naught is equal to 10 centimeters per second. Tau is equal to 5 seconds. Wait, what's tau? Oh, okay, for this equation. Right. Okay, that's no problem. The x coordinate of the particle at the moment of time 6, 10, and 20 seconds. Just have what the v is, right? Oh, it leaves the origin at equal to 0. Just integrate this thing, right? So your displacement as a vector, that will just be v naught is just some. Oh, so it is a vector as well, huh? Fine. You can integrate that as well actually. Add that as a constant. You can just take that out, and then it's just integration of this thing with respect to time. So t minus of t square upon 2 tau. Nice. And it goes from oh yeah, and at t equal to 0, your s should be 0, which is evidently true. Okay, so then you can write this thing as v naught t into 1 minus of tau t upon 2 tau, right? So that will be our formula. got a displacement. Cancel that. Okay, now what we want to find, we just want to find displacement at 6, 10, and 10 and 20 seconds. Just plug some stuff in it. So first of all, what's V naught? V naught is 10 centimeter per second. So it will be in in centimeters. Okay, so 10 centimeter per second. Okay, that times time. We don't know what that thing is. Then 1 minus t upon 2 tau. So t upon what's tau? Tau was 5, so it should be 10. Right. So start plugging things. At 6, it will be 10 into 6 into, oh, you can just do this thing, t into 10 minus 6, right? So 10 minus t, right? Exactly. These many centimeters. Then of course whatever this was, centimeter. Okay. Right. So it's along positive x-axis all the time, right? Fine. So this, no need for that. It's just along one axis. So at 6, it will be 6 into 4, so 24. So A is 24 and 24, and then what, 10 into 10 minus 10, well, just 0, and then 20, so 20 into 10 minus 20, that's negative 10, right? Oh, sorry, it's negative 200 plus, yes, then negative 200 these centimeters. Cool. The moment of time when the particle is at distance 10 centimeter from the origin is, okay, find what time that is. So D is, so when is this equal to 10? That's all you are saying. Fine. So basically, like what, 10t minus t square is equal to 10, just 10. So t square minus 10t. Oh no. Oh no. Not nice. It's not nice at all. It's the worst. Need to solve it. Negative b square root of b square 100 minus 4 is minus 40 upon 2a, so 2 5 plus minus square root of, what's this thing, 60 upon what, 4, so 50 is square root of 15. Yeah, it can't be negative, right? Oh, it can be, actually, it can be. So there's two such moments when the displacement is 10. We want when the distance should be 10. So of course the first one, because you can see initially it was positive, then it went to 0, and now it's negative. So right, and initially its rate was also positive, I think, because yeah, initially it was just v naught. So I think it should be the smaller one. So 5 minus square root 5. So that's square root 15 seconds. Next is 22. 22 is the velocity of a particle moving in the positive direction of the x-axis varies as this thing, where alpha is a positive constant, assuming that at the moment t equal to 0, the particle was located at the point x equal to 0. Velocity moves. Fine, velocity varies like this. Oh, okay, fine. Varies with this with the position. Alpha is a positive constant, assuming that at the moment t equal to 0, the particle is located at the point x is equal to 0. It's just doable. Oh, okay. So with time, that's kind of complicated because this is really bad. Because they didn't give us what the initial velocity was. Oh, actually, they did give us. Oh, sorry. Oh, sorry. What I was thinking of something completely different. Fine, and it's doable. It's just position versus time. That is the kind of equation we'll get. So dx upon dt is what I think. So x power negative 1 upon 2 dx is equal to alpha dt. Now I'll just integrate this thing. So plus 1 upon 2 divided by that. So 2 square root of x, and it goes from so initially it's 0, right? And to some x we don't know, and then just alpha times t. So 2 square root x is equal to alpha t. Nice. And what does that mean? that square root of x is equal to alpha t upon 2. So x is equal to alpha square t squared upon 4. That's the equation. Now what do we do with it? Uh, sorry. The time dependence of the velocity and the acceleration of the particle. Hey, we got the oh, so velocity as well. Fine. So our v, that should, it's just in one direction, right? Yeah, the positive x direction. Fine. So derivative of that thing is just supposed to be t upon 2 times alpha square, and then the acceleration, that should just be alpha squared upon 2. Cool. Just write that down. So position, it varies as alpha squared t squared upon 4. Velocity varies as alpha squared t upon 2, and the acceleration varies as alpha squared upon 4. Oh, so it's just constant acceleration. That's what they were saying. Fine. Yeah. The mean velocity of the particle averaged over the time that a particle takes to cover the first s meters of the path. Wait, what? The mean velocity of the particle average? Uh, so right now, by velocity, what do you mean? You mean the vector, or wait? I don't think it's supposed to be the vector. It doesn't actually even make a difference, because as you can see, x is always just increasing, right? So it will never go back. Similarly, velocity is always positive. It can never be negative or anything. So we are talking about the average velocity vector and the velocity as well. I mean the magnitude as well. Averaged over the time that the particle takes to cover first s meters. Come on, s upon the time required. That's it. So s is equal to alpha square t square upon 4. So t is going to be equal to 4. Right, it's 2 square root of s upon alpha, right? And then s upon this thing. So yeah, s upon 2 square root of s upon alpha. I think so. So square root of s times alpha square root s, what am I writing? Upon 2. That's the second part. So this was a, and this will be b, is alpha square root 2 upon s, sorry, upon square root s upon 2. This looks like 5, right? Still looks like 5, but whatever. Okay, next 23rd. Point moves rectilinearly with deceleration whose modulus depends on the velocity v of the particle as this thing. Fine. So, oh, it depends on the velocity, where a is a positive. Isn't this the same thing as previous? I mean, you will get the same equation, I guess. Initial momentum velocity of the point is equal to, okay, so it's slightly different. What distance will it traverse before it stops? Wait, what? Oh, so you, oh, this is a long question. Just do this thing. No big deal. So dv upon dt equals that. So v power negative 1 upon 2 dv is equal to a dt. Just integrate that thing. So it's like 2 square root of v, 2 square root of v. It goes from v naught to some v, we don't care. And it's just a times of t, right? Divided by 2. Just have square root of v is equal to square root of v naught plus 80 upon 2. Fine. And then what do you want with this? You want what distance will it travel before it stops. So you also want it distance as a function of time. Come on, why is this so... Wait, think about it. Why do this? Why even do this? You can just write acceleration as v dv upon dx, right? Why am I writing this? dv upon dx, and that is equal to a times square root of v. That is a much better way of solving this. Come on, square root of v. So square root of v times dv is equal to a times dx. Just integrate this thing. Well, initially x is equal to 0, right? Oh, how much it will traverse, right? I mean, doesn't really matter. You just set it to be equal to 0. Fine. So to the power of 3 upon 2, 2/3 v to the power of 3 upon 2 minus v naught to the power of 3 upon 2. That's equal to acceleration times whatever displacement is, right? And we need to figure out when this will stop. When it stops, v becomes 0. Oh, wait, what? But yeah, that's v dv upon dx for sure. Wait, how can this be? When it stops, what happens with this becomes 0, and something's just wrong about this. Initially, your v is positive. How can you have a negative x value? This makes no sense. All right, so v is increasing as this thing increases as well, right? It's probably what's happening, and that actually means key. Okay, that means that um, no matter what value of t you have, you will never have v equal to 0 for positive t at least. But what if we go for negative t values? Right. Oh, okay, it's a deceleration. Why am I so stupid? It's supposed to be the deceleration. Oh, come on. Then it's negative over there. So it should be negative vt dx. Fine, then it's negative, positive, makes sense. Gone. Just v naught. So yeah, 2/3 v naught power 3 upon 2, and that upon a, that will be your displacement. Also probably the distance, because right now its velocity is it's positive and it decreases, so at some point it will stop. In that point, till that point, it is always going with positive slope, positive rate of change of x. Good. So x will be the first value, right? Doable. Okay, so that's it. 2/3 v naught power 3 upon 2 upon a. Next question, 24th. 24th is radius vector of a point A related to the origin varies with time as this thing, where L, A, V are positive constants and I and J are unit vectors. Okay, find the equation of the point's trajectory, Y. Plot this function. Why do you want me to plot everything? Okay, let's read this. Radius vector changes like this. Okay, we want the equation of the point's trajectory. Oh no. Okay, fine. Okay, not that hard actually. So your x, that is basically, yeah, I mean like the x component of r, that is 8t, and y is equal to negative bt square. Not that hard actually. Just square this, so x square is equal to a square t square, and then divide. So y upon x square is equal to negative b upon a. So ay is equal to negative bx square. That's the locus. Right? What about this? You don't want to graph this. Oh, come on, seriously. A and B are constants? Yeah, positive constants too. Well, that means it's some kind of a parabola like this thing. Yeah. I don't know. I graphed this. So that's for the first part. So what was this once again? A. Okay. And let's do B as well. What's B? Once you have plot this, time dependence of the velocity v and acceleration w vector as well as the moduli of this quantity. Come on, just take derivatives. So why do they want us to do these kind of things? Because this is just not fruitful. It's not giving me anything. Time derivative of that thing. Okay, let's do it. A comma negative 2 pt, where this bracket has usual meaning. Okay, and acceleration, I use a, they use w, doesn't make a big difference. This is 0, and this thing is just negative 2b. There we go. As well as the moduli of these quantities, fine. So v, the magnitude, that is square root of a squared plus 4b squared t squared, and then magnitude of a, that is just 2b. That's constant. Really nice. So we got that done. Okay, let's go to third part of this. Where did it go? Wait, what question were we doing? Oh yeah, this thing. The time dependence and angle of the angle alpha between the vectors w and v. Wait, what? Between these vectors w and v. Oh, come on. So v is like this, and a is like that. So a is just the y-axis. I mean, okay, negative y-axis along the negative y-axis, and v is something like that. And v is, so it's a in this direction and then negative 2bt, so something like that, right? So just want what this angle is. Call this thing angle. What did they call this angle? Angle alpha. So tan alpha is equal to this quantity, which is of 2b times t, and then that upon this. So this thing. How big deal? Good thing they gave us the one of the vectors along the axis completely. Otherwise, you'll have to use that formula. Fine. So there we go. Alpha is tan inverse of 2bt upon a. Okay. D. Wow, how many parts are there? The mean velocity vector averaged over the first t seconds of the motion and the modulus of this vector. First t seconds. Are you serious? So your radius at t equal to 0 is 0, and then at t it's this thing. So that upon t, that's it. That's all it actually is. So that average velocity vector, that is just equal to a comma negative bt. That's it. And the modulus of this, come on, why do that? So magnitude of this vector, that is square root of a square plus b square t square. Wow. Next is 25th. A point moves in the plane xy according to the law. X is equal to 80, y is equal to whatever, but a looks familiar for some reason. So at minus a alpha t square. It's a projectile motion, of course. A and alpha are positive constants and t is time. Find the equation of the points. Come on, such silly things. You want, I mean, you gave us the whole equations. Why do you ask this? Plot this function. Are you serious? So this y is equal to x times 1 minus of alpha, and what's t? X upon a, so alpha x upon a, there we go. Which, honestly, why? Why do you want to do this? And its maximum is when x is the average of the roots, which is, so this has roots a upon alpha and 0. So a upon 2 alpha is where it's the maximum. Graph is at, yeah, so a upon 2 alpha. Something like that. This is y, this is x. And this is our curve. But isn't this obvious? Why do you want us to do this? Okay, what was this? 25th. 25th A. Okay, next we have B. The velocity v and the acceleration w of the point as functions of time. Seriously? Why? Just differentiating this thing. That's it. That's all it really takes. So v and the acceleration w of the point as a function of time. Just find what velocity vector is. It's going to be equal to a comma derivative of this. Just at minus a alpha t square, right? Yeah. So a minus 2a alpha t. That's our velocity vector. And do you want the magnitudes of these things or what? Acceleration of this point as functions of time, whatever. And acceleration is, seriously, it's just 2 a alpha, right? Negative 2 alpha. So it is 0 comma negative 2a alpha. Okay. And what else? C. C is the moment t naught at which the velocity vector forms an angle pi upon 4 with the acceleration vector. So the horizontal velocity is just constant a. Oh wait, with the acceleration that, oh, the good thing acceleration is along that, right? So it is pi upon 4 with negative y-axis. Nice. So yeah, it's basically a in this direction, and because a is the velocity in the x direction. and then a in that direction. So you just want the y velocity to be negative a. For that to happen, you would need, so 2a is equal to 2a alpha t, t should be equal to 1 upon alpha. That's when this happens. When t naught is equal to 1 upon alpha. Makes sense, right? I think so. Okay, fine. Looks good. Yeah, fine. Next. Let's go to 26. 26 is at a point, a point moves in the plane xy according to this law. Wow, where a, w are positive constants. Same kind of thing. Oh no, that's sine and cosine functions. At least something new, right? Distance as traversed by the particle during the time tau. You just gave me what x and y are. Why? Okay. Oh, the distance traveled, not. Ah, right. Wait a second. Oh, this is actually very much doable. So x is equal to a sine. Okay, there we go. We got it. X comma y. This is just 0 comma a plus well, yes, like sine omega t, and then it's a times of that. So okay, plus a times of sine omega t minus cosine omega t. So there's some phase over there. That is 0 comma a plus a times of pulsing cis. I don't want to use complex numbers for this thing. I mean, for such trivial thing, there's no need for involving complex numbers. So, oh, come on, seriously. Why do you keep on doing this to me? Is it on now? Probably not. Let's wait. Okay. So 0 comma a plus a cosine of yeah, so sine, it's negative over there. Sine of what gives us negative cosine? That minus pi upon 2, of course. So it's gonna be omega t minus pi upon 2. Because this thing is the same thing as cosine of pi by 2 minus omega t, which is sine of omega t. And sine of omega t minus pi upon 2 is not the same thing as that. Instead it's negative, so yes. That works. Yeah. And now what do we want? So it's basically just going on a circle centered at 0 comma a and radius a. Initial its phase is negative pi upon 2, so it's in like that, and then it's moving like this. Okay, let me just picture that for yourself. 26th, what do we want? Distance as traveled by the particle during the time tau. Oh, and omega t, of course. So wait, what? Time tau. Fine. What significance is, okay, so tau is just any time required. I mean, it's just, it's not some specific special thing. No, it's just any general time. Fine, it's doable. Phase changes from something to something, so basically angle. What's the change in the angle? It's just omega times tau. Yeah, that's a change in the angle. Cool. So that, there it is. You just have omega tau change in angle. So omega tau upon 2 pi times the length of the whole thing. So like 2 pi r. So basically you can just say whatever the angle is, that times the radius. So omega tau a, that would be the distance. So s is equal to omega tau a. No big deal. It's trivial in fact. It's equal to omega tau a. Tau a. Next, what do you want? The angle between the points velocity and acceleration vectors. Are you crazy? Look. Its angular velocity is constant about that point, right? About point 0 comma a. Its radius is constant. It's obvious that it's just doing circular motion, uniform circular motion. So your acceleration will just be perpendicular to velocity. What's the big deal about it? That's 90 degree. So this thing is, what kind of question is this? I thought this book had good questions. Maybe it's just not in that density, and it does have good questions, but not in that kind of density. So it's pi upon 2. Next, 27th. A particle moves in the xy plane, okay, yeah, with constant acceleration w directed along the negative y-axis. The direction of the motion, equation of the motion of the particle has the form y is equal to ax minus bx. Okay, it's the same thing as previous one. Where a, b are positive constants, find the velocity of a particle at the origin of the coordinates. So you got what the acceleration is, right? Downward. Yeah. Still, I just want to do it in the proper way. Uh, yeah. So what you have, just have negative. What do I call this? Oh, so there's no horizontal acceleration, right? Okay, so you can just take a double derivative of this time. So negative. Okay, stop with that negative. It's just d square y upon dt square is equal to. So we just take the second derivative of x first and then times. No. First we'll take the first. Let's go with dy by dt first of all. Dy upon dt, that is a minus 2bx times dx upon dt. We don't care what this thing is, right? And then the second derivative is d square y upon dt square. That is, so the rate of this thing is just going to be well, negative 2b and then d square x upon dt. Sorry, dx upon dt squared. So you got the horizontal velocity fact from this thing, and also just have a minus 2bx, and then you got d square x upon dt square and stuff. But hey, that's 0 anyway. And guess what's this? It's just negative of, what was the acceleration once again? Where did it go? Why do I keep losing track of where it is? So w is that acceleration, all right? So you can just figure out what vx squared is. Vx squared is equal to w upon 2b. Okay, that's nice. So, right, just say vx is equal to positive square root of w upon b. Will negative square root to be good? Negative square root be good? I don't think so, because look, right now when x is equal to 0, your slope is, wait, what? No, something's wrong about this. So dy upon dx, that would be equal to, right, it did this thing, right? So at x equal, right, slope is a, that is a positive number, and that means, right, your vx should be in this direction, not that direction. So your vx is constant. That's all you had to say, huh? Just put that in there and you will have your dy upon dt. Cool. Or in fact, even better, because this thing is just a constant, you can say that your x coordinate is just square root of w upon 2b times the time required. Because, yeah, and let's just say it starts at origin. Where did it go once again? Right. Okay, cool. Find the velocity of the particle at the origin of the of coordinates. So you got what Vx is. You can also figure out what Vy is from the same thing, right? From this equation. So your Vy will be, so at x equal to 0 is just a. So a times of this. So a square root of w upon 2b. I guess this is correct. What about dimension analysis? So this thing is x squared, and this is distance. This thing is also, this is distance squared. So b will be 1 upon distance. So something like 1 upon meter inverse. And then w upon b, that's meter per second square upon meters, like meter, so upon 1 upon meter. So meter square second square. So out of that is going to be meter per second. Exactly. That's velocity. So looks good so far. You got Vx, you got Vy. And what do you want? Velocity of the particle, right? In vector form, I think. So that will be square root of w upon 2b. And this thing, so 1 comma. Oh, hey, isn't a supposed, okay, a is unitless. Cool. That's it. Perfect. Okay, next question. 28. Yeah, so there are no parts for this question. Next question has parts. Just 2 till 13 will stop. Small body is thrown at an angle to the horizontal with initial velocity v0, neglecting the air drag. Find what is thrown at an angle to the horizontal with initial velocity v0. Displacement of the body as a function of time. Huh? What? No angle given. Why no angle given? I mean, yeah, you gave that there's an angle, but what is that angle? Come on, give us something, right? Initial velocity v0. Okay, neglect air drag. Displacement of the particle as a function of time. We can, if you give us what angle it was at. Oh, I think they mean initial velocity vector v0. Oh, okay, that would make perfect sense. So then I just negative g upon 2 in this direction, so it's doable. So just vt minus half at square. So yeah, a. So r is equal to v0 t minus, so g vector. I should have treated it as a g vector, whatever, g times j hat upon 2 times t squared. There we go. And b is the mean velocity vector averaged over the first t seconds. What? Oh, okay. First t seconds and over the total time of the motion. Total time of the motion, the y change, y is 0, and the next assumption is that. Fine. Yeah, so I think B is not that problematic because you just do this thing upon time and that will be it. Yeah. So your mean velocity vector is v0 vector minus gj hat upon 2. Nice. And so mean velocity vector averaged over the first 3 seconds and over the total time of the motion. Oh, it's this times time. Sorry, I forgot that. So v vector in total time, that will just be equal to v0 vector minus g hat upon 2 times the time required over time. Wait, we don't know what a total time is, do we? They didn't give us that. Okay, we need to figure out what the total time is. So it should only have horizontal component, but we don't know anything about what the vertical component is or anything for that sort. So it's not doable. In fact, we cannot figure out what capital T should be. So I'll just leave it like that. Okay, next, 29. Body thrown from surface of Earth at angle alpha to the horizontal with initial velocity v0. Assuming the air drag to be negligible. Look, this is the kind of question that I want to deal with, right? Specified alpha, v0, everything. Okay, so assuming the air drag to be negligible, find the time of the motion. Yeah, so it's just projectile motion, just a recap of that thing. Fine, so just do A. So 2u sine 2v0 sine of alpha. Right, angle is alpha, right? Yes. Horizontal, yes. So sine alpha upon g, right? This is the most fundamental thing that I remember because it makes calculation easier, right? Maximum height of ascent and horizontal range. So horizontal range isn't that problematic. Oh, and the height of ascent can also be easily figured out. Half at squared. So, right? Because look, first of all, it's at some velocity it goes up and then it goes down. Symmetric, we know that, and we can just cheat a little and say, okay, we'll start from here and then we'll go down. What's the height of descent? In fact, not ascent. So over here, the velocity is 0. That's the main thing. That's why you can use half at squared directly. So half g times capital T squared. Call this thing capital T. Actually, it should be, yeah, this is capital T. Yes, this is going to be half g capital T upon T squared. So just write that down. T squared upon 4. That's supposed to be t, and in fact the good thing is t upon 2 is just v naught sine alpha, okay, all that stuff. So basically it's just v naught square sine squared alpha upon 2 times of g. Oh, that's just g squared, sorry. Yeah, well, that cancels out, so that's why 2g. Still the same thing. All right, and what's the range? Just this time times the horizontal velocity. So that is just 2v naught sine alpha cosine alpha upon g, which I like to write as v naught sine 2 alpha upon g. And don't get confused at what this means. S and C is just shorthand for sine and cosine. I use it, nobody else does, maybe. Or maybe everybody does. Who knows? Okay, C. Wait, where did that go? Oh yeah. And at what value of alpha will they be equal to each other? So we want this to be equal to that, right? H to be equal to R. So H is equal to R implies this is equal to that. Oof. Actually, this is equal to that is better. So just have sine alpha upon cosine alpha, tan alpha. Tan alpha is equal to 4, I guess. So tan inverse of 4, whenever alpha is that. Alpha is equal to tan inverse of 4. Okay, so that's B, I think. B is done. The equation of trajectory y of x, where yx are displacements of the body along the vertical. Ah, come on. Why do you keep doing this? It's so stupid. I mean, all of this till now, isn't this just repetition of the same thing? Okay, let's do it. So what's the x coordinate? It's just gonna be whatever the vx is, which is I'm just gonna use vx at this point. So vx times the time required. And what's the y coordinate? Just vy. Just remember vx is v naught cosine theta, vy is v naught sine. I'm just gonna use it like that. It's shorter, right? So vy t minus g upon 2t squared and whatever. That's x. This is equal to y. So t is just this upon vx. Put that in there. So y is equal to vy times x upon vx minus g upon 2. So t squared, and yeah, t squared is just this thing squared, x squared upon vx squared. Cool. Makes sense, I guess. Right, and that's just tan theta, so tan alpha times x minus g upon 2 v naught squared sine squared alpha times x squared. We have seen this somewhere, right? V naught squared sine squared upon 2g. So this is actually just, well, 1 upon h, but with slight changes. It's 1/4 of 1 upon h. So basically x squared upon 4h, if that makes you remember it. So there we go. That's our equation. Y is equal to tan alpha times x minus gx squared upon 2v naught squared sine squared alpha. Right, next. Next is D. Do we have D? Yes, we have D. The curvature radii of the trajectory at its initial point and at its peak. Finally, something that is little different. So how do you find the radius of curvature? Just use the fact that v square upon whatever the radius is, that's equal to the acceleration. I mean the centripetal acceleration that they're facing at that particular point. And I repeat, centripetal acceleration. So initially it's just v naught, right? V naught, like this thing, it's some angle alpha, whatever. Yeah, so this thing is alpha. It's g in this direction, so it's supposed to be g cosine alpha in that direction and g sine alpha in this direction. This is what we'll look at because this is our centripetal acceleration. So if this is moving about a circle, I mean we assume it's moving, actually it's not, but for that particular moment, let's just say it is, then we just have v naught squared upon r, whatever that radius of curvature is, that's equal to our centripetal acceleration, which is g sine alpha. So r is equal to v naught squared upon g sin. You know what? Since we want this at two different points, it will be the best to just figure out for any point. Yes, that probably makes sense. So for any given time, you can kind of figure, okay, no, you know what? Because these 2 points are the particularly easy ones, so maybe that is why they gave us this thing. And why burden ourselves with figuring out for every single point? When instead you can just figure out uh, the whole thing, I mean, step by step for every point. It's not that hard, right? Straightforward. So this is nice. R1, call it in R1 or R naught. I like it like that. V naught square upon G sine alpha. Right, cool. And we also want what is R peak. So at that point, this is just the horizontal velocity, which is so it's like V naught cosine alpha squared. So that will just be V naught squared cosine squared alpha, constant C squared alpha, upon the acceleration. The acceleration is G, not G sine alpha. So that's it. Okay, so that's D for you. 1 point is 30, it's 230 as well. Using the conditions of the foregoing problem. Oh, so that this problem, I think, draw the approximate time dependence of moduli of the normal. What is this? Wn and tangent Wr acceleration vectors. We had to do it, as well as the projection of the total acceleration on the velocity vector direction. Why? Okay, on the velocity vector direction. So you want normal and tangential. Well, good thing velocity is always tangential for this thing anyway. So whatever is the tangential acceleration vector, isn't that the same thing as the projection of the total acceleration on this thing? Or is it different? Because as much as I remember, your velocity vector is along the trajectory all of the time, right? It has to be. Okay, this is going to be a big thing to do. Okay, but it's better than doing nothing at least. Oh yes, 30. So first of all, we'll need the velocity vector, right? So the velocity vector will just be Vx minus g times t. Sorry, whatever. Vx comma Vy minus gt. Okay, that is how it's moving like that. And then at that point, what is the angle? Angle is, let's call this the theta. So theta and theta is just Vy minus gt upon Vx, right? And what we need to figure out is, so this thing is g in this direction, that's our actual total acceleration. It's always just that all of the time. So along the velocity vector, oh, it's negative, weird. This thing is going to be 90 minus theta, so sine theta basically, right? Something missing right there. Wait, last time what did we do? We did g sine alpha. When this thing was alpha, we basically did yeah, so this thing was theta, and shouldn't it have been g cosine alpha? I think we messed up somewhere. Wait a second. Right, that's moving it v naught like that, and see alpha with horizontal, it's g in that direction. It's supposed to be 90 minus alpha over there. This will be alpha, so it's supposed to be cosine alpha. Sorry, then this should be cosine alpha. Doesn't matter all that much. We just need to figure out what this acceleration is. That's just going to be g times cosine alpha, and this thing is going to be g times sin alpha. Sorry, theta, not alpha. Cool. Yeah, and what do we want? Yeah, just these things. So no problem. Acceleration normal is in magnitude. We want the magnitudes only, right? modular amplitude proportion. Yes. On the velocity vector direction. Wait. What velocity vector direction? Are you kidding? Are you serious for? So you can just directly use this theta without specifying what it actually is. Are you serious? No, I will go a step further than that. So yeah, the normal acceleration, that's just going to be g cosine of theta. We know what tan theta is, right? Just draw the triangle for this thing. So vy minus gt, and this is just vx. So yeah, this thing. So our sine, no, cosine theta will just be vx upon square root of well, vx squared plus vy, so just v squared. So v squared and then plus g squared t squared, or instead just go with magnitude of v at that particular point. So yeah, magnitude of v vector at that time. Okay, this t probably means tangent. Should not use this. Yeah, I will figure it out at that point. So the thing is, like, vx remains constant. Okay, scrap that. Just use what they want us to use. It's not going a step further. It's just complicating it even more, because it's just easy to figure out what this angle is, right? So just use this angle directly. So it's just this g cosine of theta and g sine of theta. That's it. So 30, the normal acceleration is equal to g cosine of theta, and the tangential acceleration, which is the radial acceleration. Wait, what? Tangential is WR. Oh, it's T, sorry, it's not R. Uh, it's the same thing as acceleration along the velocity vector, right? Oh, so now I understand what they wanted. So they didn't. Okay, wait, what? As well as of the projection of a total acceleration vector. Wait, they want the projection and not. Uh, yeah, whatever. So just do 80. We don't know what that actually means. Why do they want projection of that while they already gave us the tangential acceleration is this thing? So hmm, fine. And also theta is just tan inverse of Vy, which is just V naught sine alpha. Sorry, sine. Come on. V naught, yeah, sine alpha initial, the minus GT upon V naught cosine alpha. There we go. Okay, next. Why next is done. 30 questions. That's it. Wow, there's just so many of these. Will take forever to do this. Fine. So I'll see you guys in the next video.